Hello everyone. I wanted to go over this problem that comes up every now and then in a typical Calculus 2 course. This problem is interesting because there's actually two ways to do this. You can either do this by U substitution, which I'll show first, or integration by parts, which I'll show last. But the most interesting thing here is that you get two different answers. They don't look anything the same. But of course, how does that make sense? How can an indefinite integral with no limits here, have two different answers? Well, as it turns out, long story short, kind of a spoiler alert, it has to do with the fact that plus c is a different plus c with each case, so they're kind of the same up to adding a constant. Let's see that first. So let's tackle this by u sub. We're going to look at this inside here and say, okay, that's good motivation to maybe let that be u. So I'm going to let u equal 2x plus 1. So the du is its derivative, 2 times dx. And that would mean 1/2 du replaces our dx here. Okay, so now the integral looks like this. X times the square root of u times 1/2 du. Now the 1/2 you can pull out, that's fine. And the radical u is u to the 1/2. So I'll do that. Now the issue here is this x. You don't want to mix x's with u's when doing u sub. You want to turn all x's into u's. So you want to convert this x integral now into a u integral. So to do that, I'm going to go back to our original definition here. And I'm going to say, okay, well, u is equal to 2x plus 1. Can we find x in terms of u? And you can. Notice if you subtract 1, you get 2x. Dividing by 2, we get x is equal to u minus 1 all over 2. So that actually extends this box here. I usually box all of our substitution items, and there we go, that extends that. So now I can replace this x with that result. So I'm going to do that here. Kind of move this over a bit. Okay, so that's going to be replaced with u minus 1 all over 2. Now, of course, this is the same as 1/2 times u minus 1 times the quantity u minus 1. So 1/2 times 1/2, when pulling that 1/2 out, you get 1/4. Distributing this u to the 1/2 in, you just add the powers. So notice the power here is 1, so 1 plus 1/2 is 3/2. Minus 1 times u to the 1/2 is that. And we have 1 over 4 on the outside. And this is I made a slight mistake here. For some reason I wrote dx, but this is the same du we had over here, okay? So I just wanted to emphasize that these are du's, not dx's. My mistake. Okay, so now we can take the antiderivative of each of these using power rule. Remember how that works? You add 1 to the power and then divide by the new power. Dividing by a fraction is the same as multiplying by the reciprocal of the power, so we end up getting this. And of course we have that 1/4 on the outside, and then we write plus c. Then we can back substitute using our substitution. So in fact, I'm going to distribute at the same time. So 1/4 times this, that's going to be a 1/2 times 1/5 because of the cross cancellation you get there, or 2 over 20, you can think of it like that. 2 over 20 is 1 over 10. And u was 2x plus 1, so this is 2x plus 1 to the 5/2. Okay. Minus 2/3 times 1/4, that's 2 over 12, which is 1 over 6. U, which is again 2x plus 1, to the 3/2. I'm not going to check this, but you can indeed check this is indeed an answer by taking the derivative of this and showing that it's somehow equal to the original integrand, x times the quantity, or x times the square root of the quantity 2x plus 1. Okay, great. So that's an answer. Now I said there are two answers. So now I'm going to use integration by parts. In particular, I'm going to use this method known as tabular method, which will just speed up the process so this video isn't too long. So when doing integration by parts, you pick something to be du, or I guess something to be u, my mistake, and then something to be dv. Now, I'm going to pick this to be u and this thing to be dv. And the reasoning here is because, and by the way, dv is the entire radical, okay, not just the inside, but the entire thing. And the reasoning here is that the derivative of what we're letting u be, x, has a derivative that's eventually 0. The derivative of that square root will never be 0. The radical kind of stays imagine it's all to the 1/2 power. You bring it down, and then you get negative 1/2 and then negative 3/2, and the power never gets to 0 actually. Okay, but with tabular method, what we're going to actually do is we're going to create this table where u is our derivative column and dv represents our antiderivative column. Okay, so our u was x and our dv was the square root of 2x plus 1, which I'm going to write like this, 2x plus 1 all to the 1/2. And I'm also going to use some knowledge of u sub that will also speed up the process. Okay, so remember, you take the derivative for tabular, you take the derivative of the derivative column, so x, until you get 0. Derivative of x is 1, derivative of 1 is 0. And now we have to take the antiderivative of our second column until we arrive at this row. So how do we do that? Well, I'm going to ignore the inside and just say the antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2. So I want to do that, but with the inside. So the inside is 2x plus 1. So this is 2x plus 1 to the 3/2 multiplied by 2/3. Now, because of u substitution, if u is equal to the inside 2x plus 1, kind of like we saw on the left side, the derivative of 2x plus 1 is 2. As a consequence, we have to divide by 2. So I'm going to multiply by 2/3, but I also need to divide by 2, and that's because derivative of the inside is the constant 2. So that's kind of a quick shortcut you can use to take the antiderivative, kind of skipping u sub. So that same idea again, antiderivative of something to the 3/2 is that same something to the 5/2, okay? And then divided by 5/2, and also divide by the number in front of x on the inside, which is the derivative of the inside, which again, you can only do that when the derivative of the inside is a constant, so that works here. And from the above, we had that 1/3 as well already. Okay, so we're not done. For tabular, we have to multiply diagonally like this and change signs accordingly. Here we don't change signs. Here we do change signs. So using the tabular method, our answer right away is the following. It's 1/3 x times 2x plus 1 to the 3/2 minus, let's see, that's 1 times 1/3 times 1/5, that's 1/15, times 2x plus 1 to the 5/2. Okay, plus c. Now clearly these are different answers. They look definitely different. Similar, but different. And the thing is, okay, so first off, they're both answers, and they're both correct answers too. Now, they're different, but they are kind of the same. They both work. Their derivatives are both some form of the original integrand. So now I'm going to show that these are the same. And the way I'm going to do this is by factoring. Okay, so I'm going to take the first one, I'm going to factor it, and the second one I'm also going to factor it, but individually. So let's look at the first one in detail. So how I'm going to factor this is I'm going to, it's a little tricky, but I'm going to look at the lowest power, which is at 3/2. So I'm going to pull out 2x plus 1 to the 3/2. And in doing so, what we're really doing is we're basically subtracting everything on the inside by 3/2, or the powers by 3/2. So for the first term, that power is 5/2. 5/2 minus 3/2, it's a plus, is 2/2, which is just 1. Okay? For the second one, the power of 3/2 minus 3/2 is 0. So it looks a little strange at first, but if you distribute this, you'll see that it is actually correct. Right? You can kind of see it. 3/2, if you distribute back in, 3/2 plus 1 is 5/2, and 3/2 times this is, well, 2x plus 1 to the 3/2 anyways times that is the second term indeed. Okay, so I hope that makes sense. Now, I'm going to actually keep, so we have this plus c on the outside. I'm going to keep actually factoring. I want to get rid of these fractions because they're a little bit of a mess. So what we can do is we can multiply and divide by the LCD, the least common denominator, which I guess here would be 30, right? 6 goes into 30 and 10 goes into 30. So I'm going to divide by 30 and multiply the inside by 30. So notice 1 over 10 times 30 is just 3, and 1 over 6 times 30 is 30 over 6, so it's 5. So again, if you distribute this, you'll see you indeed get the same thing above that's boxed. And now that we have 3 times this, we can distribute and then combine. So notice here we get 6x plus 3 minus 5, which is the same as 6x minus 2. This simplifies a little bit. Notice here we can actually factor out a 2. So we get 2 times 3x minus 1, and that 2 will actually cross-cancel with this to give you 1 over 15. So I'm going to write our answer factored now as 1 over 15 times 2x plus 1 to the 3 halves times a quantity, 3x minus 1, plus a constant. Okay, so now I'm going to do the same thing. I'm going to try to factor the next one, and then we're going to compare, okay? So let's look now at our second answer here. This guy, there we go. And we'll factor it in the same way, and we'll see we'll get something very similar. Let's see if it works. So the smallest power is 2x plus 1 to the 3 halves. I'm going to factor that out. The way you do that is you subtract each power for these newer terms on the inside of these brackets, subtract each power by 3 halves. So you get 1/3 x for the first one, because 3 halves minus 3 halves is 0, 2x plus 1 to the 0 is just 1, minus 1 over 15, 5 halves minus 3 halves is 2 halves, which is 1, so we get that to the 1, so we've seen that before. We have plus c here. Okay. Great, so now what? Well, now the least common denominator here would be 15, so we can pull out a 1 over 15 and multiply the insides by 15. 1/3 times 15 is 5, and 1 over 15 times 15 is just 1. So that distributes, and we get 1 over 15 times 2x plus 1 to the 3 halves times 5x minus 2x minus 1. Okay, now of course that's 3x minus 1. Now I said they're the same up to adding a constant. Let's see what these are. Well, they're exactly the same actually, interestingly enough. So in fact, yeah, I kind of actually misspoke then, I guess, earlier when I said that they're the same up to adding a constant, which could actually happen as well, but in this case, that wasn't actually the case. They weren't the same up to adding a constant. They are actually the exact same. So these are, they're even the same C. But again, at face value, once you look at the answers before the simplification, those boxes above, they look pretty different. I mean, they look similar, like I said, because you still have 2x plus 1 to those powers, but yeah, the numbers in front are different. One has an x in front. It looks a little funky. Okay, so thank you all for watching. That concludes this video, and I'll see you in the next video.